Hello everyone, welcome back to my video series that I'm doing for my wireless communication and convergence network class. And for this video, I will be discussing signal propagation and path loss models. So what is propagation? So propagation is the way that signal propagates from the transmitter to the receiver. And here on the top figure, you can see there's the transmitter and here's the receiver. And so the signal is characterized by power. So from the signal that is transmitted from the transmitter is always constant, but not for the received power. So it really depends on the receiver. So when the receiver is steady or there's no velocity that affects it, then the signal that is received will be a much better quality. And here on this figure below, we can see that the y-axis of the graph is dependent on the power that is received, all because, as I said, the transmitted power is constant. And the distance that between the transmitter and the receiver determines the x-axis here. And as you can see, the power diminishes exponentially as the distance rises. And so the blue line here is an indication of this, which it also indicates path loss. And so here, the red block or the red line, it indicates that an item that generates a non-line of sight scenario to the signal. And so as you can see in the red line, the graph depicts a changing intensity of the power received, all because of these obstructions. And so of course, when there are multiple refractions because of obstructions such as buildings, walls, and other solid objects, the change in received power has ripple effects. So for path loss, there's no real obstacle that will affect the signal. But as for shadowing, which is the red line here, and the multipath fading, which is the green line, these obstructions affect how the signal is received. And so the key to the amount of power that the receiving size will receive will all depend on how strong the signal is, on how far the distance is, and the amount of obstacles that the signals face before reaching the receiver. Okay, so for path loss modeling, there are many solutions when it comes to this, which include the Maxwell equations, which, well, it can be considered complex and impractical. Free space and two-path models, too simple compared to the Maxwell equations. Ray tracing models, which require site-specific information. Single slope path loss exponent model, which is good for high-level analysis. And finally, measurement base and standard models, which unfortunately are not very accurate, but it can also be used to assess different designs. Now, the Maxwell equation here looks at the interaction of the electric and magnetic fields, which will then be combined to form an electromagnetic transmission. It is, however, extremely difficult and ineffective to use. And as a result, a simpler approach such as the free space and two-path models are suggested to be used. But then again, as I explained before, they can be quite simple. And I will explain further Now, in the model of an open space or line of sight model or free space model, this refers to signal transmission without any obstacles in the receiver's path, so a direct transmission from the transmitter to the receiver. So there will be no obstacles such as the curvature of the Earth, buildings, and other things. And in general, the free space model states that power drops are proportional to the inverse of the distance squared. And it is also proportional to the lambda or wavelength squared, and is inversely proportional to frequency squared, all of which are produced by the antenna's effective aperture. Okay, next we have the two-ray model, or yes, the two-ray model. So the receiver in the two-ray model receives two sorts of signals: the LOS signals and non-LOS signals, or the go and not go signals. The non-LOS signals are caused by reflections, refractions, and among other things. According to the two-ray model, the power declines in proportion to the squared distance. And when the distance is larger than the threshold distance, the power falls substantially or very far away. And it is also said that in this model, this model is independent of wavelength and frequency. Next, we have the general ray tracing model. So general ray tracing takes into account the reflection, scattering, and diffraction phenomena. So from the figure on the left, you can see that due to many reflections or refractions, the receiver may receive many signals from different sources. So this general ray tracing model takes into account all of the problems that were addressed. And in this model, reflections generally dominate the transmission web. Yeah. So, and finally, general ray tracing requires site geometric and dielectric properties. But it is considered to be easier than Maxwell. And for this model, computer packages are also often used. For simplified path loss, so simplified path loss is the simplification version of the path loss model. It's used when path loss is dominated by reflections from objects. And so here you can see in the equation below, gamma is the most important parameter for the path loss exponent, and it's determined empirically. So for the gamma, it ranges from 2 to 8. And here in the equations, the PR stands for the receiver location. P is the reference point to the receiver location. PR is the power that is received, and PT is the power that is transmitted. Okay, so how do we overcome all the problems that comes when we are trying to propagate a signal? So all these problems can be used by using an empirical model. So in the area which are not suitable for millimeter waves, the existing channel modeling cannot be used. So the early cellular empirical models are based on extensive measurement, and the examples include the empirical path loss models, the Okumura model, the Hata model, the COS231 model, multi-slope model, Ballfish or Bertoni model, and many more, which I will not include here. And the disadvantage of the empirical model is that it's quite dependent on the location of the experiment. And for example, the Okumura model is conducted in Japan, where there are many obstructions, such as the buildings and the geography of the country. And current cellular models include LTE and 5G, and Wi-Fi channel models are also included. Okay, here we have the millimeter wave spectrum. So the millimeter wave is located in the high spectrum bandwidth, which is the green area here. So from the image, here, the spectrum starts from the top left up here, down here to the bottom right. So this figure is based on the United States standards. So in the US, you can see here that for example, the 5G network is located in the 38 gigahertz spectrum. And since it's very high on the spectrum, it's located down here near the millimeter wave spectrum. And for lower networks such as the AM radio, it falls quite low up here, quite low up here in this spectrum right here. So as I said before, the millimeter wave starts from here up to here. So it ranges from 60 gigahertz to 100 gigahertz. And since millimeter waves work in high frequencies, so getting bandwidth will be much easier compared to when it's in the lower frequency spectrum. Right. So millimeter wave actually needs more research and more experimenting, as its channel models are still considered to be immature. So it is classified as so due to the fact that there are few accurate analytical models which based on measurements. So the relationship between path losses and the square of the wavelength is huge, and it has oxygen and rain absorption as well. The figure shows the power attenuation, which is on the y-axis here. And so the higher it is, the worse the attenuation becomes. And as for the x-axis, it indicates the frequency. And so the figure shows that the attenuation in the 6 gigahertz range is particularly high due to oxygen uptake, and in other cases shows water or rain peaks. Okay, that is it for my brief explanation on this topic. And thank you all for watching, and I'll see you next time.